take a spectrum of a star and figure out, oh, it's 5,000, sorry, is a much more reasonable one, degrees Kelvin. Or we could look at interstellar space and realize, oh, it's 2.7 degrees Kelvin, which is how that temperature of interstellar space was figured out originally. And now we're going to do a quick rundown. Composition is really great because we were able to figure out that all the stuff we're made of and Earth is made of is all the same stuff we see out there in the night sky. And so we're not missing any elements. We're not dealing with two different environments. This is all the same stuff, which is a huge thing to discover at the time. And we can also study atmospheres, which is really exciting. We can learn more about Mars and Jupiter and all the other planets in the solar system, or even the atmospheres of planets not in our solar system that we can detect with radial velocity, which leads me to radial velocity, which is one, how we find planets around other stars, which is very cool. And we can also study just the motion of the stars themselves. And so we can figure out how galaxies move and where we're going, all that kind of stuff. It's very great. And then we've also got temperature, which is very important for the cosmic microwave background, which is pretty much just the fact that the Big Bang was very, very hot, but it happened a very long time ago. So everything's cooled down a lot since then, but not to nothing. And so we can still detect that remnant of the Big Bang, and that is the cosmic microwave background, or that little bit of heat, that 2.7 degrees Kelvin, that interstellar space has temperature. And so this graph is actually also the cosmic microwave background, because when we call it a temperature, that's the average, but each spot in space has its own little specific temperature. So the bluer spots are actually colder, the redder spots are hotter, and from that we can get a lot of insight into how everything worked back then and how we started out. So the beginning of the universe, a very, very active field of study right now. And now we're going to talk about how it works, because it's cool, we can do all these things with spectra, but if we don't know how to make one, then what are we even doing? And so we're going to talk about how you turn a star into a spectrum, basically, and that is with a spectrograph. And so this is just a rundown of the basic components. So once you have your telescope and you set it all up, it's going to focus all the light to a specific point. And that point is what we call the entrance slit. And from there, that light is passed through a collimator, which pretty much just makes all the light rays parallel and a lot easier to work with. From there, we send it into a grating, which is very similar to a prism. It takes all the light in and splits it up into rainbow colors. So then we can get all of those frequencies separated so we can see which ones are where and how it's all set up. And then we have our focusing camera, and that just spreads everything out nicely so that we can see what's going on. And then from there, we just have our spectrum. And there it is. And now we're going to talk about a very specific spectrograph, and that is the McKellar spectrograph. And so this plaque is actually just outside the door to the spectrograph room, and it details McKellar's various discoveries and contributions to the DAO. And this is a basic floor plan. So this is in a paper published right after it opened in the early 60s. So we can see the original layout. And it's still largely unchanged. We have here. There's also a computer room here that they hadn't done the whole computer thing yet. And so then we also have the spectrograph room, and the telescope is up here. It sends all the light down to the spectrograph room. We've also got a dark room, and that is because they used to take spectra on film. And so they'd have to develop that film in the dark room. And that dark room is still there. It is now a storage closet. Yep. Well, you know. And now the specifics of this one. So you might notice a few familiar components, and all the rest of it is pretty much just putting the light into a convenient place for the room so that we can get it into the spectrograph without too much hassle. So first, light comes in from the sky, and it hits the primary mirror, and it goes up to the secondary mirror, and then down into the polar axis, which is that slanted thing that holds the telescope up. And then they send it over here, and then down through the floor into the first floor. and then over to the spectrograph. And so then it goes through all the same pieces we talked about. And so that's where it's in the spectrograph room. And so next, we can see some of the actual images, because surprise, surprise, the components don't actually look like the little white lines I've drawn on this diagram. So you can see what it actually looks like. So this here is that fifth mirror that goes right into the spectrograph. So we have this tube here. The light goes down through the tube. It hits the mirror, and it goes all the way over that way, which we then follow over here. And so just behind this panel here is the entrance slit. But before that, we have a couple extra little instruments that we can use. So first off, this here is a guide camera, this red thing. And so what it does is it siphons off a tiny little bit of the incoming light, and it uses it to tell us where we are, so that you know, okay, I have everything nice and centered on what I want to look at, and you can adjust things, make sure the telescope is properly positioned, and then you're not wasting your time taking data that's out of focus or just in the wrong spot. Very useful. And then we've also got this here, which is the calibration lamps. And those are great because when we take light in from the star and we get all those nice spectral lines, we don't get a handy label that says, this line is 737 nanometers, which is what you need for all the math to work out. And so what this does is we have gases of known compositions in those lamps, and then you flick one of them on, and then you run all that light through the same optical configuration as you're sending your data through from the stars. And so from there, you know, okay, we know these elements have these wavelengths of emission lines. And then from there, you can correlate that to the lines you're getting from the stars. And then we also have, then the light goes into the entrance slit. And then on the other side of that is this. We have the entrance slit on the other side. The shutter is closed right now. And then we've also got this mirror here, which can direct the light to various points in the room. And then the spectrograph itself, we have first, light comes in, it goes all the way back, it hits the collimator, and then it goes over to the grating, which is here, and we can actually see how it's making rainbows out of all that, just the overhead lights in the room. And so it does a very similar thing with the light from the stars. And then it sends all that over to our focusing camera here, and then to the smaller image plane here, where we can then take a picture with a camera, and that's your spectrum. But there's also another spectrograph. So this is a 2-for-1 deal. You get 2 spectrographs in the spectrograph. And so we have a longer focusing camera and a shorter one. And what that does is the longer camera can split up the light more, so you can see a lot more details. But if you're doing something that doesn't need quite so much detail, you can also cut down on a lot of the processing time by just using a shorter camera. So it all very much depends on what you're looking at and what your project needs are. So there's a lot of customization that's available. And then lastly, this is just a cool through the years of the long camera. So we can see here McKellar is posing with it in the 50s while they were constructing the spectrograph room. And then we've also got a picture from that paper in the early 60s showing it. We can see the image plane here and the camera. And so back when they were doing that with film, that's where the film plates would go. And then nowadays, we have it right here. Kind of cool to see what's changed and what's entirely the same. And now we're going to talk about all the various really cool things we've done with spectroscopy here at the DAO. So first off, right when it started, this is how film spectra would look like. So this one was taken in 1918, and this one in 1921. And you can see the calibration lines like we would get from those lamps above and below. And then right down the middle is the spectrum itself with all those lines right there. And then the first thing that I'm going to mention here is a map of the Milky Way. And so this was created with the Plaskett telescope because the McKellar hadn't been built yet. So this occurred in the 20s, 1921. And what they were doing was they took hundreds of stars and they took radial velocity measurements of all of these stars over time so they could track how they were moving. And from that, we were able to tell not only where we are in the galaxy, which is right here, this dot here, you can see the label sun, just barely, but also how everything is moving, so that our galaxy is rotating and that we're actually orbiting around the galaxy. Very slowly, but we are. And so that was a huge deal at the time, and it's very exciting. And that was all done with radial velocity. And now, the discovery of the first exoplanet. So Dennis mentioned this a little bit earlier, but this was not the first confirmed exoplanet, which was 51 Pegasi b in 1995, but this was the first discovered. And it was retroactively confirmed in 2003, but it was first discovered in 1988. And so that was done by a team consisting of Bruce Campbell, Gordon Walker, and Stevenson Yang, who's actually a current UVic professor and still does a lot of work on the McKellar telescope. And so what they did was they did a big survey of a lot of bright stars in the sky using this telescope. And they took all these radial velocity measurements, and they were looking for that little wiggle of the lines as these stars orbited their center of mass with all the planets. And what they found was the star Gamma Cephei A, which had this planet, Gamma Cephei AB. The B stands for exoplanet, basically. And so that was the first exoplanet that was discovered. And this is, full transparency, not an actual image. It is an artist's interpretation, but it's based very heavily in studies that have been done on the composition of the planet and various things. And so this one is pretty fun. It's only 45 light years away, which is a long way, but compared to some things, it's really close by. And it's 9 times as big as Jupiter, which is already huge. It's the largest planet in our solar system by far, but this planet is 9 times as big. And that is really interesting because that's actually, the radial velocity method is very biased towards finding these huge planets because they cause a bigger wiggle in the stars because the center of mass is further from the star and more towards the planet. And so they're easier to pick up. And now we're going to step towards the future a little bit. So this is a bunch of equipment that sits on the test bed at the McKellar. So there's not only are there 2 spectrographs in that room, there's also a testing bed for a new instrumentation that's being developed. And so what they do is they will sometimes get time on the telescope and they will test all their new instrumentation and then go back and fine-tune it even more and keep working on it. And so this is the current status of the REVOLT project. And REVOLT stands for Research, Experiment, and Validation of Adaptive Optics with a Legacy Telescope. You can tell a lot of those words are lowercase so that the acronym works. And so what it's doing is adaptive optics, which is pretty much how we undo the effects of Earth's atmosphere. Because the atmosphere is great. It protects us from all this solar radiation, but it's also a lot to look through when we're trying to look at the stars, because all that light has to be bent through, kind of like when we look at a water glass and the straw is all crooked. It's that a billion more times. And so what we want to do is get rid of that effect so that we can see much clearer images from here on Earth. And so this is actually a before and after image. So here we have Arcturus, a bright star you can see pretty well in the night sky in the constellation Boötes. And this is before adaptive optics, and this is after. And so you can see just how much of a difference it makes. And so I, for one, am really excited for all the advancements that are being done with adaptive optics right now, and excited to see what all they can find and keep working on here in the future. And so that is all I've got. If anyone has any questions, I'd be happy to give them a shot after this. Thank you.